Welcome to Logical Verification 2020-21. This video is about Chapter 11, Section 5. We're going to take a first look at quotients. In the last video, I've shown you two ways on how to take an old type and construct an exciting new type from it. I mean, either by the subtype construction that we looked at in the last video, where we take a predicate on the type and then construct a type consisting only of those elements that satisfy this predicate, which is the subtype. And now we're going to look at the quotient, which identifies some elements in the type. So if we say that we want to identify some elements, it means that we need to tell Lean which elements we want to identify. And this works via a so-called equivalence relation. So if we have some type here, and we want to identify all of these points on the left and all of these points on the right, then we're going to give a relation to Lean that according to which these elements here are equivalent. Equivalent here, and also these ones here equivalent. So, as a relation, this is a relation function from alpha to prop. However, what we are going to give Lean is instead a setoid object. For the quotient construction, Lean uses the setoid type class, and so here a setoid on alpha, and a setoid is just a type equipped with an equivalence relation. So the setoid alpha just contains the equivalence relation plus a proof that it is an equivalence. Okay, so what do we get then? What we will construct then is a quotient. And the quotient then contains 2 points. One for the left class and one for the right class. And we get a function that maps each of these points here to the corresponding point, the quotient. So this one here quotient of the setoid, and this map here is, let's draw some more arrows here. And this map here is called quotient.make. It has the nice notation with this fancy brackets here. Okay, so this is how you write down the quotient type, and then you get a function that maps from the old type, that maps the elements from the old type into the quotient, sending it to the right point here. And the important part about quotients is how the equality looks like on quotients. The idea that you want to keep in mind is that the equality on the quotient, so the property of 2 elements being equal in the quotient, this should be the case if and only if they are equivalent in the old type, using the equivalence relation that we provided. Now, I didn't tell you what an equivalence relation is yet, and the properties that we require from the equivalence relation really stem from this property here that we want to have about the equality of the quotient. if you think about it, any relation such with this, any relation here that satisfies this property needs to be reflexive because equality is reflexive. It needs to be symmetric because equality is symmetric, and it also needs to be transitive because, again, equality is transitive. So if we want to give a new equality to a type, which is in a sense what the quotient construction does, also the equivalence relation needs to satisfy these properties. And indeed, the definition of an equivalence relation is that it needs to satisfy these three properties. It needs to be reflexive, it needs to be symmetric, and it needs to be transitive. Not nearly enough space here for transitivity. So let's just write transitivity here. Because these are the three properties. Again, if x is equivalent to y and y is equivalent to z, then x is equivalent to z. Okay, so these are the three properties that an equivalence relation needs to have. This is the definition of an equivalence relation. And if we put such an equivalence relation into a setoid, we make a set of type class, then we can take the quotient of the setoid and we get this construction here that identifies all the elements here. And well, since it's an equivalence relation, the relation also holds of these points here by transitivity and by reflexivity. We also have these loops here actually. Okay. And another way to think about this is as the equivalence classes on the original type. So we can also think of this as taking a partition of the old type, and then each point in the quotient corresponds to one of these equivalence classes here that partition the old type. So equivalence classes. Equivalence classes. An equivalence class is just a set of all points that are equal to each other via the equivalence relation. So we have one equivalence class here and one equivalence class here. Okay, so this is like how quotients look like in the picture. Let's look at how they look like in Lie. So there is, first of all, the quotient constant, which, as promised, it takes a setoid and then constructs a type for you. Unfortunately, quotients are somewhat special. You cannot define them yourself. These are built into Lie itself. So you cannot write them down using an inductive type or a structure or anything. You really need to use the built-in support in Lie for this. Okay, so this is a quotient. It takes a setoid, and as promised, a setoid is a type class consisting of a relational helper, as well as a proof that this relation is an equivalence. An equivalence relation is a relation that is reflexive, symmetric, and transitive. It needs to have these properties because it will become the equality on the quotient, and the equality, no matter whether on the quotient or on something else, is always symmetric, transitive, and reflexive. Okay, so then I've already shown you the map that goes from the old type to the quotient, and this map is called quotient.make, and it takes an element of the old type and then goes to the quotient. So maybe it would be more interesting here to put an X in front of it so that we actually see not just meta variables but actual names for these things. So quotient make is defined for any alpha, for any sort alpha, for any alpha, and a setoid on alpha and then it takes elements from alpha to the quotient. Okay. So now we know how to construct elements of the quotient, but we still don't know that actually the equality on the quotient corresponds to the equivalence relation of the old type. So for this we have two lemmas in Lean. So one of them is quotient.sound, which says that if two elements are equivalent on the original type, then they are equal on the quotient. And the second one is quotient.exact, which goes the opposite way around. So which says that if two elements are equal in the quotient, then they are equivalent in the original type. If you put them together, you get exactly what I've shown you on the drawing. That equality in the quotient is the same as equivalent in the old type. Okay, now we know how equality looks like on the quotient type, but we still don't know how to define functions on the quotient type. So how do we define a function from quotient? Well, if S is a setpoint on alpha, and we want to define a function going from the quotient to some other type beta. We still don't know how to do this because there is no way to get an alpha out of a quotient. There is, in general, no function from quotient S to alpha, at least not a canonical one that we could define for every quotient. So we need some additional definitions for this. And in order to define a function on the quotient, we are first defining a function on alpha. Okay, so maybe I should draw this. So if we now want to have a function that we choose here. So now I have another type here, and I want to define a function here from the quotient to this new type, to beta. Then what I first do is I define a function on alpha. So well, let's say that we map here everything to this one here, and then also everything to this one here. So we map all the elements in alpha to this one here. And what we then get via quotient.lift is a new function, namely the lifted function, from here to here. So in order to define a function on the quotient, we are first defining the function on the alpha, and then lifting it to the quotient. Okay, so this clearly does not work for all functions from the original type. So if, for example, we said that, oh, we are just mapping this one to one element in beta and the other elements of this equivalence class to the other element in beta. So here. Then we cannot lift this function. Why? Because where should this element go here? Should it go here? Because we sent these to this point? Or should it go here? Because we sent this point to this point here. So what we need in order to lift a function from alpha to the quotient is that the function respects the equivalence relation. That in a single equivalence class, it does not send some points to one output value and other points to another output value. because then we could not define the function of the quotient, which needs to pick one output value for the single point in the quotient. Okay, so in order to lift, we need a function f prime, which is defined on alpha, and which has the property that for all x and y, if x, is this that box? Yes. If x and y are equivalent, then f prime of x is equal to f prime of y. And this is exactly what quotient.lift does. Let's put an at here so that we can see this more nicely. So quotient.lift, it takes the function on alpha and beta and a proof that it returns the same output value for equivalent inputs, and then we can lift it to the quotient. So if you have a function on so if you have a binary function that has two arguments in the quotient, then you could also use quotient.lift. You could use it twice to define a function with two arguments in the quotient, but it is much more convenient if you use the quotient.lift2 function. Which, if you look at it, it takes a function. So if we want to define a function on two quotients, like this one here, so the S1 quotient, which is on alpha, and the S2 setoid, which is on beta, and if we would then want to define a function on quotient S1 and quotient S2, then we do this by giving Lee the function from alpha to beta to phi, plus a proof that it returns the same output for equivalent inputs. And then we can lift this function. So maybe you're now wondering, okay, I have this quotient.lift function. How do I actually know that it does the right thing? That like what I showed you on the drawing here, that the output that we get, so that if I go from one point here, if I go from this point here to the quotient and then apply the lifted function, then I get the same as by taking the function from alpha to beta. So this is true by reflexivity. So if you apply quotient.lift to quotient.make, then it automatically is equal to f of x by reflexivity. So in the last lemma we want for quotients is that there are no more elements in the quotient than the ones that we can create via quotient.make. That is, every element in the quotient is quotient.make x for some x, and this is the induction principle on quotients. So you can look here. We can, if we have any property on the quotient, then this property is true if it's true for all quotient.make